Good morning, ladies and gentlemen. The witching hour is here. We've slipped slightly already, which is probably a good idea of how we'll carry on. But I'd like to start off by welcoming you on behalf of my colleagues in the BRE Centre for Fire Safety Engineering. Welcome you to Surgeons Hall and expressing our thanks to you all for being here to help celebrate a significant milestone. The Ruby anniversary, if you like, of fire safety engineering at Edinburgh University. We're very proud of what has been achieved over the past 40 years and feel it is appropriate to pause and take stock, review where we are at the moment, and start considering what direction we should take in the future. The two-day symposium also provides us with the opportunity to bring together our alumni, who we hope will feel the same pride in the knowledge that each one has played a part in our success. And it's been very interesting standing at the door downstairs, greeting the alumni from 40 years ago and identifying them. I think I recognise just about all of them. I think I have a bit more hair than many. The symposium programme has been developed to cover as much as possible of the full range of the relevant sub-disciplines within fire safety engineering. The range of topics is very broad, from smouldering to the behaviour of structures in fire. And with the exception of the medal lecturers, the speakers have been selected from either current Edinburgh University staff, graduates from Edinburgh, or long-term research or educational partners. It's hoped that discussions during the next 2 days will help us chart the course ahead. I've got to interrupt what I say here by giving the announcements of a domestic nature, where the loos are. They're downstairs. More important, because this is a fire conference, we have to talk about fire alarms. There are no tests scheduled for the next day, so if you hear a continuous bell ringing, you'll know that we've got to get out. And the fire exits, I feel like an air stewardess, that way and that way. If you go that way down the stairs we came in and out into the courtyard, if you go out that way you end up in the street behind Surgeons Hall. The toilets are downstairs, reasonably accessible. There is a lift if anyone feels that he can't walk down the stairs to get to the loos. It's just through there. We're fortunate to be in this part of the building, because if we had been in the old part of the building, I would have had to advise the ladies that they'd have to walk about 300 yards to get to a loo, because lady surgeons didn't exist in 1840 or whenever it was. Coffee and lunch will be served coffees will be served directly downstairs, and I believe lunch is over in the hotel, just off to the left as you exit the building from the way you came in. Wi-Fi access information is included in the delegates' packs, which you received at registration. And if any of you require assistance, don't ask Luke, don't ask me, because we don't really know anything that's going on. Ask one of the people in red shirts. They're very, very good at their jobs. I think there's one more thing I have to mention, and that is the dinner tonight. And I'm not going to say anything about that, because Luke will be summarising the day's events at the end of today, and will give you details of where we have to assemble. Okay, to move on. We're delighted that we've been able to incorporate into the symposium 2 prestigious lectures, each of which are associated with an annual award. Tomorrow, the 2014 Philip Thomas Lecture will be given by Professor Colin Bailey on the topic of structures and fire. Sadly, Philip Thomas passed away in January of this year, but he'll be long remembered for his seminal work at the Fire Research Station, which laid the foundations for the discipline of fire safety engineering. This morning, the symposium opens with the 2014 Rasbash Lecture. This was established by the Institution of Fire Engineers over 10 years ago as an annual lecture in memory of David Rasbash. we're very pleased to host this year's event on the 40th anniversary of the programme that David Rasbash led until his retirement in 1982. I'd now like to hand over to Martin Shipp to introduce the 2014 Rasbash Lecture. Martin is representing the Institution of Fire Engineers, of which he is a trustee and a board member, although his day job is Technical Development Director for Fire Safety in BRE Global. It's particularly appropriate that he is with us today, as he is also celebrating a Ruby anniversary. He joined what was then the Fire Research Station 40 years ago. Martin, over to you.
Thank you very much, Dougal. Thank you. Right, well, it gives me great pleasure to represent the Institution of Fire Engineers here today. As Dougal says, my post on the board of the IFE is to represent fire engineers, to try and maintain balance with the preponderance of fire officers, as well as a lot of you will be aware, on the institution, and to recognise, of course, the important role that fire engineering is now seen to hold within the institution, which, of course, sounds a bit weird. We are the Institute of Fire Engineers, but, of course, when the body was founded nearly 100 years ago, fire engineering isn't what we think of it today. As far as I can work out, and that's a bit of a struggle, their idea of fire engineering was how to take a water pump apart and put it back together again, and what size of hook ladder to use in a particular incident. I guess things have changed quite a lot. Obviously fire engineering has become increasingly important over the years. As Dougal says, I find it interesting. Perhaps I didn't appreciate the importance of it at the time when I joined the Fire Research Station, that fire engineering was in its infancy. We were doing work for governments at the time on things that were called deemed to satisfy. Later on we discovered that was fire engineering, but at the time we didn't know that. But as the discipline developed, and I guess the important thing was that over those 40 years, Professor Rasbash and the department that he founded, and of course other similar organisations around the world, have helped develop our understanding of fire, both as a sort of general phenomenon, but also in developing the knowledge base that is so essential for us to actually do the work that we aspire to do. As Dougal says, the Rasbash Medal was introduced both in recognition of all the work that David Rasbash did, but also to provide the opportunity to recognise preeminence in the world of fire engineering. There's a number of medal holders in the audience today, so welcome to them. I guess we almost ask ourselves, to what extent have we been successful as a profession? Very difficult to judge. I mean, one of the things that fascinates me over the years is what are our key performance indicators as a profession. The fact that we're all here, sitting here today being employed, I suppose, is one indicator that there's something in fire engineering. There's a job to be had. Most fire engineers seem to be able to walk into work, so that's a good thing. Whether it's good beyond that, the only thing I can say is that I guess we're all aware that over 40 years the number of fire deaths has steadily gone down. I remember memorising way back in 1974 that the number of fire deaths in the UK was 1,000 a year. I think last year it was somewhere between 200 and 300. So we've managed to make substantial inroads somehow, and I'd like to think that fire engineering has been a contributory factor towards that. And of course those statistics are reflected around the world. So I think that it now leads me to welcome John to give the Rasbash Lecture. As you're all aware, the medal is only given as a prize for producing an important lecture on fire engineering. You don't get it for nothing, so there's a little job to be done first. Most people know John. I don't think I need to say much about him. I was intrigued to see that his first degree was in electrical engineering. He then moved into applied maths, doing work on flame spread, which I guess was probably quite a novelty in those days to think that mathematics might be applied to flames. I understand that he joined FM Global in 1966 and has been there most of the time up to now, and is still assistant vice president with that organisation. And of course in that time he's played a major role in developing fire engineering and fire science that underpins fire engineering, looking at flame spread, pool fires, the development of computational fluid dynamics modelling, or the underpinning knowledge that goes into that, and of course flame radiation and heat transfer in flames. A lot of the key issues that underpin the knowledge that we use in actually doing our day-to-day jobs as fire engineers. So I'm extremely pleased to welcome John and invite him to give the Rasbash Lecture. Thank you.
Oops, sorry, wrong one.
There he goes. Thank you.
That's you.
Great. Good. I feel very honored to have been invited to give this talk. I'm engaged. I'm going to be presenting to you new research, right? And it's a wonderful opportunity to try to communicate about radiation and incomplete combustion. It's a subject that when I was employed by Factory Mutual, now known as FM Global, about 48 years ago, as a matter of fact. So I've been working, and I had taken on inside myself the challenge to understand these flames. And so this is a lifetime of work that I'm giving you the most recent results. This is a real opportunity. We have about in 1983 or so, David Rasbash came into a laboratory in which I was working, and we were measuring the volumes of pool fires that we were supplying at different rates. Gaseous pool fires. And it was a particular memorable meeting. Here David was coming up, and he immediately recognized the nub of the problem. And you people who know Dave realize that he always got to the nub. And the question was, what's the volume of the fire, and what relationship does it have to the overall heat release of the fire? And we both believed that they were proportional. We thought, or guessed, they were proportional. But we didn't know that. They were very difficult measurements. It's very difficult to measure the volume of a pool fire and the flames. So this sat. We measured it, and we had the data that showed that they were proportional. But the various theories at the time didn't say so. The various theories we're saying that the volume went with a 6/5 power. And so this work just sat there not being understood, gnawing at me, okay, up until about 5 years ago. And then I began to understand it. And so I presented a paper a year ago or so, showing what the mechanism of the buoyant turbulent diffusion flames, and showing that it was a Rayleigh-Taylor instability. Now, you guys probably don't know what that is, okay? But a Rayleigh-Taylor instability is when the gravity works on the flame itself. The individual flamelets, the Rayleigh-Taylor instability, turns them over, and this is most intense the smaller the scale is for these buoyant, truly buoyant flames. And so this is the action that actually causes the combustion, because it twists around the flame and gives a straining rate that causes the combustion. And this Rayleigh-Taylor instability drives you can see from theory and from measurements that in this paper you can see that the Rayleigh-Taylor that this is most intense. And once you realize that it's most intense at the scale of the flamelet scale, then all of a sudden all this other material becomes more or less obvious. Okay, the whole thing becomes obvious that the burning rate per unit volume should be roughly a constant. We get a number similar to the number that David suggested. Now we get so this is the heat release rate, and what you get is this is the scaling time, which is related to the buoyancy and the diffusivity, the gravity and the diffusivity, but of the local flamelet. That's what's driving these flames. All right, and now the radiant fraction, because the radiant fraction is independent of the fire size, and the incompleteness of combustion is independent of the fire size. These were known empirically. These were known empirically for a long time, but we didn't have an explanation for it. And so now with this study, we have an explanation, and now I go forward. So the purpose of this thing is to go forward to see and understand better what these radiant fraction and incompleteness of combustion are. And I actually hope I work you a little bit, okay? And so you'll see some equations here. And so I'm going to go forward, and but I want to show you very briefly what we're going to cover. We got the Rayleigh-Taylor instabilities. I've just discussed that. You have the smoke point, which characterizes the sootiness of the fuel. Then we have we present as sort of a diagrammatic way of looking at the flames in terms of their temperatures, etc. And then we put some mathematical model here. It's a simple model, but basically you still need some mathematics to get it to be really quantitative. All right. Now we make a comparison of the model with experiment and air, and you'll see that we do a pretty good job with that. And now we do some correlations, and we're interested in not only in burning in air, but we're interested in burning in other atmospheres where the temperatures can be quite a bit different. All right, the flame temperatures. And now we express this at the very end, the radiation absorption coefficient, in terms of some very simple variables: the heat of combustion, the air to fuel stoichiometric mass ratio, and the smoke point height here. We make some recommendations. So that's what I'm going to give you. And now we will go forward. I want to just give quickly some definitions. Most of you know what a radiant fraction is. I assume you've been in the fire field. You know that maybe many people assume it's 30%, but it does vary by the type of fuel for these big turbulent flames. Then you have the convective fraction, which is the stuff that goes off, and you'd measure it high up with the thermocouples, the amount of convective material coming off the fire, and convective heat. All right, and this is the incompleteness of combustion. That would be the remaining unreacted chemistry that leaves the fire zone. Okay. So conservation of energy says these are the only three things that it can be. So we add them up and we get the total heat release rate. Now we divide through by M the total rate of combustion or supplied combustion, theoretical combustion here. We divide through, we have the fractions equal 1. And now we just look at this equation, and you will see this equation in different forms many times in this talk here. Now, finally, I want to just introduce, in terms of definitions, that's a heat of combustion. That you have, this is the enthalpy rise over the ambient enthalpy. It's the thermal enthalpy rise here, and for the flame. And this is the heat of combustion per unit mass of fuel. This is the total mass of combustion products per fuel mass. So that's the stoichiometric ratio. So now we have just some basic definitions, which I'm hoping that most of you are familiar with. If you are, then you should be able to hopefully understand much of what I'm going to talk about. Now we're going to try to give you what is the smoke point. The smoke point, all right, this flame is just at its smoke point. We show 4 flames supplied at different fuel supply rates, coming off you could say a little gas here, or it could be candles, but having different flame heights. And the smoke point is the maximum height which just does not release smoke. Well, here I have it just a shade above, and you can see the smoke coming off, just a little trace of smoke coming off above this flame. And for this particular fuel, this will be the smoke point flame height. And so that's it's well known. We know also that this characterizes the rate of soot formation in for that fuel burning, in this case, burning in air. So it's the rate of soot formation, or the rate at which the soot is being formed here is characterized by the smoke point, and it's correlated in a very simple way by inverse to the inverse of the smoke point. So the rate of soot formation, and we see this plot here. All right, this is a plot is where we show the incompleteness of combustion here, the amount of the fraction of the chemistry that didn't get burnt of the fuel, and this is the release of the soot particles, or particulate release, the energy contained in those. So the chemical energy contained in those. Okay, so now this is correlated by the inverse, so we get smokier and smokier fuels as you go this way, and this is an empirical correlation. I cannot explain exactly why it follows this logarithmic relationship. However, it's an empirical relationship. It comes from all the release measurements were made by Archie Tuarson at FM Global in his FPA, and all the smoke point measurements, these were assembled by Yee and Sunderland from many different investigators. And so the scatter, I think a certain amount of the scatter is experimental scatter. Because it's from many different investigators, and so you see, but the correlation is really pretty good. Now let's understand. Now I want to understand a little bit more what this fuel is doing, what's going on here. This one is supplied with not enough fuel to reach the smoke point. What happens is a certain amount of soot is being produced in the flame, but the ability for the air to oxidize it, not that much is produced, and the air can be oxidized by the oxygen, and it gets all oxidized, and then you have no further smoke coming off here. This one, you've increased the fuel flow rate, but you've also increased the fraction converted to soot because you've given it more time. And so now it goes up here, and here the air and the oxygen can oxidize this, and it just manages to oxidize all the soot that was being generated. Here we supply it with even more fuel, even greater fraction is converted into soot, and the air is insufficient to oxidize it. We get this amount, and here we get a copious amount of soot coming off because it has the highest heat release rate. A very important thing to know and to understand even this talk is to realize from our measurements that if you were to measure the effective temperature at this point, and you measure the effective temperature versus height, the effective temperature at this height, if you actually have some flame there, is about 15 or 1600 degrees Kelvin. So the temperature versus height remains invariant to the overall fuel supply rate here. Of course, here it never gets down. Here it starts off at 2200, let's say, Kelvin, and it drops down maybe here to 19 or 18 100 degrees Kelvin here, and then all the soot is burnt out. So here, because the temperature drops below 1500 degrees Kelvin here, it can no longer oxidize the soot, and so the oxidation is turned off at about this height, and for this for this fuel here. So that's where the smoke point height, at the smoke point height, the flame in this case is about 1500 degrees Kelvin. Okay, and that's a very important number, by the way. 1500 degrees Kelvin or thereabouts is the temperature at which oxygen can still be decomposed and forming OH, which then oxidizes the soot. All right, so this is a very important. It's really controlled by the ability of the oxygen to be destroyed at the higher temperatures and form OH. So that's okay, I'm going to go forward. I've summarized here the very important inputs for this entire discussion. These were known for 30 years or so, 25 years, 30 years. Now I want to give you the first picture, really, of this particular study here. All right? And now we're only interested in looking at the flames in a global way. We want to understand, with every time throughout the study, we're looking at the flames, we're interested in how do you characterize the overall flame in terms of its radiant fraction, its release of soot, or incomplete products, its various characteristics. So I'm going to look at it. And I'm just giving you a typical situation. We have diffusion flames, we have air. I sort of make it very simple with fuel here and air, and now we have a diffusion flame, and this is sort of like this is the so here you have the maximum temperature, and this is the characteristic maximum temperature for the burning of the flame. This is the characteristic radiative temperature of the soot. Okay, that you soot and actually gases, they also radiate. So it's a characteristic temperature, and this is an average temperature, a time average temperature. But soot and radiation, you have to take the fourth power. You all know that the radiation goes with the fourth power of the temperature. So you take the fourth power and you weight it by the fourth power. Well, the higher temperatures get more heavily weighted, and so therefore you are up here. And it turns out with a little simple integral, when you have a very simple way of looking at the flames, you get these numbers. If you implement the fourth power, you get the number, the TRF, the temperature rise is for the flame radiative temperature rise, the effective T to the fourth one, is 3/4 of the maximum diffusion flame temperature. And so we build this in. This comes from just looking at the flame, recognizing that the radiation is not coming only from the top of the hottest point is coming from something somewhat below, and now trying to get this to be roughly meaningful from a quantitative viewpoint. TRF is actually, at a given point in the flame, you can measure TRF. It's a measurable quantity. I'll show you. You call it a Schmidt temperature. And what we have is we have a flame here, we have a black body oven here, it has a certain radiance going T to the fourth, it has this radiance that's coming out, and if you view it from this radiometer, if you didn't have the flame, you get a certain radiance from the oven, it would go all the way out through here. If we put a flame in between, then there's an absorption some of this radiance is going to get absorbed by the absorption coefficient, the length L that it has to go through, and the Stefan-Boltzmann constant there. And so some gets absorbed, so that gets subtracted. But the flame is also radiating, and if the flame is radiating at its TRF temperature, or to the fourth power, and therefore we have we subtract something and we add something, and when you subtract and add the same amount, so you wind up with the I oven, then you've balanced it, and you know that what the effective TRF is. So this is just simply to give you a picture that that this really does have some measurable meaning. Of course, the flame, you have big turbulent, buoyant flames, have many different heights, so the average temperatures vary a bit with position. But I'm just giving you, this would be at one position, you can make one measurement. Next slide. We want to look at this from an energy viewpoint. So we want to it's fairly simple. We have the peak temperature in the flame, peak temperature there is reduced because there's been a lot of radiation. There's a chi-R. So we reduce that temperature, and that's, if we have the overall height here being unity, and chi-R then is the fraction the fraction that is radiated, and this fraction down here is what is going to be in the flame or going up and out in the case of chi and the convection. So this is the fraction that's radiated, and this is the fraction that stays within the flame while it's burning. Eventually it releases, above the flame. Now, so that's the point of this graph. We showed you the 3/4 here, and now we just implement this. This is the energy supplied per unit mass of you burning heat of combustion. I defined this. This is the ambient enthalpy. This is the increase. HCH minus H naught is the increase in enthalpy, which would be delta H, the heat of combustion, divided by 1 plus S, which I showed you before. And this is the convective component that is not radiated, and we have our simple relationship we have the Cp times T convective minus T naught up here, which would be that, but this is 3/4, TRF is 3/4, and I have to put this 4/3 power in here because there's a difference between this temperature and this one is only 3/4 of that one. So here we have the radiant fraction expressed in terms of this simple relationship. And again, we're going to be looking at something like this equation over and over again as we go through in this talk. Now I want to, here we're looking at it again. This is the governing equation expressed in physical terms, in using physical variables. But in order to really be able to look at this, it's also, by the way, I was trained as an applied mathematician. And when an applied mathematician goes and looks at physics, he's always going to put it in the dimensionless form. Always. Because you can see things, because it simplifies it, and you can see certain things that you get confused by all the symbols with the physics. We can simplify it, reduce the total number of symbols, and so that's what we're going to do here. And it's important because we can introduce physics as we're doing this. We introduce the 1500 degrees Kelvin. That's a critical temperature. It's a temperature at which the oxidation of the soot can, above that temperature, the soot can be oxidized. Below it, it cannot. This is the corresponding H reference. This particular number I've chosen very, very carefully based on empirical evidence. And I choose this number here. It relates to whether a flame will release soot or won't, or smoke, incompleteness of combustion. So we basically, it's a carefully chosen number that makes all this modeling work. And this is the dimensionless temperature. So this is the 1500 or whatever. This is the whatever the characteristic flame radiation temperature is divided by this reference temperature. If this is greater than 1, the soot is going to get oxidized. If it's less than 1, some of it won't get oxidized. All right. So this is the ambient temperature, the ambient supply. This is the heat. This is effectively the dimensionless heat released by the combustion or the supplied heat by the combustion process per unit flame mass. And so now that we insert these variables in here, we just insert them in mathematically, and we get here, instead of 1 minus this, we have 1 minus this. This is the energy supplied. This is the convective energy released here. And if I multiply through by this term here and just simplify, I get this is the related to this, the total enthalpy above absolute zero minus the enthalpy that relating to the 1500 degrees Kelvin. If it's greater than 1, this will be greater than 1, and if it's and all the soot will likely be oxidized, and this is the supplied energy. So this is the radiant fraction. It's a very simple expression, and I think it hopefully it actually helps in understanding this talk. Now we go forward now I'm going to apply it to the radiant fraction. And this is the last introduction well, I will talk a little bit about mathematics, but this is the last real physics that I'm going to be introducing here. Okay, with equations, that is. The radiant, this is the total, if we have a given fire, it has a total heat release Q dot. What fraction of this is released in the form of radiation in all directions? Okay. This is the area, the total area, global area, looking at the flame. And this is the radiation per unit area. This is a fairly standard way of reporting. We got T to the fourth. We have a reference temperature because the ambient is radiating back at T naught. So this is the excess over the ambient radiation and T naught, which is very small numbers, okay? But we just put it in just to be careful. Okay, this is the effect. This is a certain amount of the heat doesn't escape the flame because it gets self-absorbed, and this is the absorption coefficient. And so we have this. If I have a very long path length, this will be small, and this is unity. But if I have a very short path length, the length over which that flame is radiating will be less, and there will be less radiation. So this gives me effective path length. All right. The overall heat release rate is the flame volume times the heat release rate per unit volume. So now this number, which Dave Rasbash would love, is here, and multiplied by the volume of the flame. Now we have the radiant fraction again, and what I'm going to do is I'm going to divide Q dot. I'm going to divide QR by this term here. So I just divide it, and I wind up QR. Yes, AF is in the numerator, and now we have VF in the denominator here after I've divided through. So now I recognize, one recognizes is the area over the volume, but we know that the volume over the area is something called the mean beam length. And people who have been working a bit in radiation know that this is a common sort of thing. It's like the hydraulic diameter type of thing, and you have the factor of almost 4 here. 3.6 is an approximation due to it's an effective approximation that works for many different geometries. And so this is the mean beam length, and so I have the area divided by the volume is 3.6 divided by the mean beam length, and now I simply insert that in here. I multiply and divide. I am going to multiply and divide by the absorption coefficient here. In here, so I divide here, I multiply here, and I can substitute for this volume over the flame area. I can substitute the mean beam length, so I have it here. So this is my expression. It's a simple way of looking at it globally over our flame. And in the case of a very short path length, this thing goes to unity, and so we just get this expression here. And this is a key absorption coefficient which is needed for practical purposes. If you want to actually calculate radiation from flames, and you know the flame length over which the radiation, or but you got to know the absorption coefficient to actually predict radiation. All right, we go forward. I note here, the flame radiation comes from both soot and gases. You've got to be aware of that. If you had no soot, you still would have some flame radiation. All right. Okay. So now I'm just going to combine that last slide. I just incorporate this term in here into the mathematical expression. And so I have the same sorts of things, but I just define this as U, capital U, and this is like a dimensionless absorption coefficient. All these terms are known except for the absorption coefficient, kappa. Okay, so here, so this I know the reference, I know this, I know the Stefan-Boltzmann constant, so I know these terms. And so now I have U, and I put this in dimensionless terms, and I insert it in here. This would be the effective t to the fourth, and this is the ambient, and this is the absorption coefficient. So now I've extended the equation to include the radiant fraction expressed this way, the radiant fraction expressed this way, and the radiant fraction finally expressed in terms of the actual absorption coefficient and the emitting particles. All right, next. Now I'm going to define a term. It's a very important term for this entire presentation, and I call it mu. Okay, and what it is, we take this expression here, the radiant fraction expression, and I want to look at the meaning of the zeta, or the temperature, and so I take a term which I say the temperature, I make this unity here, and I subtract this unity here, and then I just correct it by having 1 minus unity here, 1 minus zeta here. Okay, so now I define this term as mu, but mu can be interpreted purely in terms of physical quantities that I know. This I assign, I know this number, H reference, 2.79 kilojoules per gram of flame. This is the heat of combustion, the supplied heat of combustion per unit flame mass, and so this is an expression for what mu is physically. So I know it physically. So that gives me a type of reference, okay, and it's related to the supplied chemical energy. This term here is, if zeta is less than 1, I'm going to have means that the flame temperature, the effective radiative flame temperature, is less than what it needs to be if all the soot is to get oxidized. So that means some of the soot isn't going to get oxidized. So somehow it's related to the incompleteness of combustion. I can only say that I'd expect the incompleteness of combustion to be proportional to this. But it turns out, for some reason, that I don't have a proportionality. It comes directly out, and we'll investigate that further. Okay, so we have this simple expression that the radiant fraction is equal to the supplied excess plus the incompleteness of combustion. It just turns out that this expression is not only proportional. I'd expect it to be proportional, but I didn't expect it to have unity there. All right, but that comes out of the study. So that's our definition of mu. And chi-IA, I can express it, and I just take the same equation here, and I say chi-IA is the maximum of either 0 or the radiant fraction minus mu. So if the radiant fraction is a little bit bigger than this, then I will have some incompleteness of combustion. It has these 4 properties. Hopefully you've read them. Okay, I'm saying the same thing. Chi-R is a linear function of mu. That's an empirical fact. Okay, it is approximately. I'll show you that later. Okay, it's approximately a linear function of t. Adiabatic is that's not exactly a straight line, but it is almost. And mu is a function that I show you here of these quantities here. All right, so it's. Well, that's as much as I can say about it at this point. Now, we're going to look at 3 cases. First case, where the flame radiation temperature is very high. There, the soot gets oxidized. Next, a more normal situation. The radiant fraction is less than 0.2. The incompleteness of combustion is less than 20%. And the radiant characteristic flame radiative temperature lies between these temperatures. All right, and the peak temperature of the flame is greater than 1500 degrees Kelvin. These numbers here, by the way, I have a few measurements of numbers, but I don't have a lot of measurements of numbers. But this all makes sense in the picture that I have of the flame chemistry, because remember, these flames, it's not so easy to measure. It's just like the volume is difficult to measure, and we just have an image of these flames. I'm presenting a simplified image of these flames in order that we can get a picture of of what's going on. So I put these temperatures here because we know this temperature is important for the combustion, the 1500 degrees Kelvin. So we put this in. We know we get a lot of data that guides us. So for the aliphatic hydrocarbons, what are aliphatic hydrocarbons? Methane, propane, propylene, simple hydrocarbons, chain hydrocarbons. And now below, where we get copious soot, we get really ugly-looking flames. Almost all aromatic fuels are of this nature. They have the benzene ring. And anybody who has a chemistry background automatically knows it, and people who don't have a chemistry background may not know it, okay? But basically, they fall in these categories here. An example, polystyrene is a very copious, sooty fuel, and that has an aromatic ring in it. Benzene has aromatic rings, so those are examples. All right, so now we're going to look at the case one. Case one, the complete oxidation of soot. Well, the characteristic effective radiation flame temperature is greater than 1500 degrees Kelvin. That means the soot, the characteristic temperature of the soot is greater. There's plenty of energy, chemical energy, the thermal energy there supplied. So I can now, and before the flames finally die away, they will oxidize the soot. And so that sits up there, and that's a simple situation. I have my relationships. This is the radiative loss. I have a higher temperature. I sort of imagine we have excess oxygen in the air, and so we have this situation here. Not much soot. Not that much soot. And if you put a little oxygen in the air and burn methane, you won't get any soot. And even methane gives you very little in the laboratory, but big fires you get a lot. Okay. Next slide. This is case two. Now this is the most typical case. You have the aliphatic hydrocarbons. You have all the fuel decomposes in the flame. You see none of the original fuel coming out of the flame. None of the stuff. It all goes up in there, and the carbon, and some carbon forms, and some soot doesn't oxidize. Okay. The effective flame radiation temperature is below, so all luminous flame have soot in them. Okay, that's what makes them luminous. But in this case, some of that soot just didn't make it, didn't get oxidized. So because the temperature was a little bit too low. And these are sort of typical numbers here for effective flame. I've measured a couple of these with George Markstein. So we have this situation. I was always interested in the temperature of these flames, but it's not easy to measure. But we got some measurements for ethane and propane, and we got some measurements, and they were in this region, 1350, in that range. All right. We also, I'll go next one. Whoops. Oh yeah, I want this one. Okay, so let me go back just a little bit here. I want to take you. Okay, I want to take you to this equation. This equation, we have this, and we have this term here, and this term here. Okay, and I'm going to apply this, and we're going to look at this experimentally with experimental data. All right, and I've given you an interpretation. These are for the first two, case one and case two. Case three we'll talk about in a minute. Okay. Now, here is the case 2. All right. Case 1 would be there would be no incompleteness of combustion. So in case 2, we look at our flames. These are good measurements here, and it's remarkable to see that this modeling. So this is methane, ethane, propane, ethylene, propylene, and it's a pretty good match. We just take of this equation here. These are all measurements, so I'm pretty happy with that. All right. Now when we get a large amount of soot formation, problems arise. All right, and we're going to have to. We're not quite so certain, but we can interpret them a little bit. We got some big help. For the next slide here it gives me a big help. In 2004, Archie Tuarson published a paper in the Fire Safety Journal, and in there, he showed the radiant fractions. These were all measurements he did in the FPA, and what he did, I have to tell you, he supplied heat from the heaters, all right, and he measured the incompleteness of combustion. He measured the convective release with thermocouples inside the duct, right where it went into the duct. And he now added those up, subtracted the supplied heat by his heaters, and then he came up with, you'd have to say, estimates of the radiant fraction. And so he has the radiant fraction, but the incompleteness of combustion, there were good measurements there. And so what we were interested for a long time, what happens when you have the incompleteness of combustion that gets to be significant here? What causes it to tail off? What causes it to eventually decrease? And both he and I were fascinated by this for years. And he finally went ahead and made some measurements. And I was really very surprised to see it. And what he did, he took some really ugly fuels. He put, halogenated things. They were really ugly. They sort of, I wouldn't want to be near them. And he took these ugly fuels and he made these measurements. And so what we see here, and this is his curve fit. This curve is Tuarson's fit. I just put a line through it here, just to see and just to show it linearly decreases down to this 80%. Above this, of course, it's so incomplete that 4/5 of the fuel never burns, never gets oxidized. So it's really ugly here, and you wonder how a flame can even work there, and you wonder that the thing is so sooty that when you look at it, you barely ever see a flame, even in a little experiment. So this is so you have some flames. Otherwise, it wouldn't burn at all. So something gets above 1500 degrees Kelvin. But most of the stuff is just black stuff that immediately decomposes at low temperatures as it's being heated, and so it just decomposes, immediately forming soot. And once it's forming soot, the soot has a big molecular weight. It doesn't diffuse, and it just sits around and is super lazy, and it doesn't get involved in the flames. So it bypasses the flames. Okay, and so now we just have to somehow we need to model that to get some idea. So that's what we have here. I have an approximate model for this. The copious soot formation, case 3. It decomposes, much of it, if not all of it, decomposes at low temperatures and bypasses the flame. When it decomposes, some of the lighter species, like hydrogen, H2, or other things, float off to the flame, and the soot remains behind. And so it's not a very pleasant to think about it. It's not a very simple situation. But here we have the case, empirically, you begin to get this bypass after 20% incompleteness. And here, with the model, the zeta, according to our model, the model says that our zeta, we're only going to be at 1200 degrees Kelvin here. this is at or less than 1200 degrees Kelvin. So this is at 12 or 12 roughly, or equal to, at 1200 degrees Kelvin. Now, if it drops below 1200 degrees Kelvin, by this simple diagrammatic model, it means the convective temperature is below 1500 degrees Kelvin. That means you definitely don't have complete combustion, because even the flame is going to get extinguished in parts, partially extinguished, because it's not hot enough to get oxidized. So obviously it's fluctuating, so some is above and some below. But so this picture is of a flame that's sort of limping along. You expect to get some clumps of real soot in there coming out, and that's actually been measured. That they measured that you get some of this relatively cold soot, even in the flame region. Okay, so that's the idea. We now model this, and this model is not completely perfect by any means, but I say that anything above 20% is bypassed, goes out, and so this is the fraction that never burns and never even gets involved in the flame, and then I insert that fraction in here. We take our equation. I'm not going to. Okay, and we just manipulate this equation. I still have the same heat release supplied energy term here. It's approximately this, even though some of it gets bypassed. Also, the oxidant ratio gets reduced because the remaining stuff that does burn, I have less of that. So now I have same terms in here, and now I apply my equation, but in this case I have to apply it this way. This is the material that was bypassed, and so I finally, and I say, but the material that is not, that does burn, I can't really drop much below 1200 degrees Kelvin or for TRF. So therefore I have this expression here, and I apply that, and I get this. This is what this model is predicted, but the empirical thing, the empirical equation says, Archie's empirical result tells me that it's going to be this. So I apply this expression. I just had to put in this 0.8 and increase this term so that it works smoothly. I make it smoothly continuous, and I have it here as continuous, but here I had to introduce the 0.8, and that's an empirical introduction that I don't have a good theoretical explanation for. And now we take this and we apply this, and this is surprisingly good. Consider acetylene, has 50% radiant fraction. We measure that many times, and we got up there. 50 can be even a little bit more at times. Acetylene, and this is really very surprising that I can predict this well with the approximate model here for the bypass material. So I'm happy. This is a very important result of the thing that we have. We can, knowing the incompleteness of combustion, which can be measured in the FPA rather readily, and we can then the radiant fraction cannot be easily measured in the FPA. It's a difficult measurement to make. You have to make it at a bigger scale with radiometers, and it's more difficult. But the incompleteness can be measured, and therefore, from the incompleteness, and knowing the heat of combustion, and knowing the stoichiometric ratio, if you know the chemistry of the material that's being burned, you can determine the radiant fraction, but you have to empirically measure the incompleteness of combustion, which tells you it relates to the smoke point. If you know the smoke point, you can do this. So you can start with a smoke point or an empirical measurement of the incompleteness of combustion, either way. So now I'm going to give the final part of this lecture. This is a very important result, and we have some more things what we know. These are some very interesting measurements that we did about 30 years ago, 20 years ago, that here the we measured the radiant fraction for 6 aliphatic hydrocarbons, and they all turned out. I cannot. This shows the extent of the measurements. We vary the oxygen and nitrogen in the ambient, and we add sometimes nitrogen to the fuel itself, so we can vary mu over a wide range, and to see that, and they all turn out to be linear, and it's really surprising how linear it is, these measurements are. And I just indicate the part in air, where air lies on these curves. Okay, so these are some measurements. The quality of the measurements you can see, or the quality of the correlation and the measurements together, it's really surprising to get a comparison that is that. This is the deviation of all fuels, all measurements. There are many, many measurements here, and with that formula that we had up there, this is a weak dependence on the stoichiometric ratio. That's weak, but this is the principal one is this mu, and that's what's shown here. And this is the radiant fraction in air with the difference in mu and from air, and these are differences from air, which would be given with the dots. And this is an effect which isn't shown on this graph, the extent of it, but it's small, but it's measurable. And there's some good theoretical reasons why it has this form with the stoichiometric ratio. All right. Now I take our original simple equation, or a simple equation of mu and the temperatures, and for these gases, and I take the measurements, and I just apply the radiant fraction. I know what zeta, I apply an equation. I have to go back all the way to 12 to get there. Sorry. I forgot to put it on this slide. Okay. So I apply just simply this equation here. All right, I apply this equation here, and when I know the radiant fraction, and I know what mu is, and so then I infer what zeta is here. I infer zeta, I get mu, and so with these two equations, I get that expression of the flame temperature. So I know the flame temperature really rather well. There we go. I know the flame temperature global. These are global temperatures rather well. And you see as the energy increases, as the supplied energy, chemical energy increases, or the excess energy is increased, the temperature goes up. But it levels off at lower mu, and it levels off at about 1200 degrees Kelvin. And this is 15, and they lie just below. For methane, it lies just below the 1500 degrees Kelvin point. And so there's our thing. This is the adiabatic. I just put the adiabatic temperature versus mu. It's almost linear. We go next slide. This is, I now incorporate, I take this equation, so I now introduce what U is, and I solve that. I know my radiant fraction, I know my effective temperature, and so now I solve for U, and U goes, it loops up like this. And this is the absorption coefficient. And the absorption coefficient at low temperatures, soot, is hard to form. It doesn't form very rapidly. At very high temperatures, there's chemical reasons to believe that it doesn't form very well, because for chemical reasons. But also it gets oxidized more readily at high things, so you'll get less. So some of it's due to oxidation. The chemistry, the fact that we're really looking at different chemistry here, the different fuel chemistries, is shown clearly by these somewhat different curves. They're not all the same. Okay. And that's chemistry, which I have nothing to say about. I'm not a real chemist that looks into all these individual reactions. So this is the area for the chemist to gradually understand. Now we we find the last slide, the last piece of work here, is I said, well, we had this thing here. What can we do in terms of understanding? What can we do? And I tried to fit a formula based on my intuitive and my various understanding of this. And so this is my formula that I would apply if I had to guess. And I plotted out this formula here, and for this value of this absorption coefficient. But the advantage of this is that it tells me about the various characteristics of these flames in terms of the smoke point. And so if I start with the smoke point, I don't even need the incompleteness of combustion. I can come up with this result for another fuel, a solid fuel or something. And you can determine the smoke point of a solid fuel. It can be routinely. You can do that actually in the FPA. So you get the incompleteness, you get the smoke point, or I could directly put the incompleteness in here. Either way. And so now we can get the absorption coefficient, which is needed for applications. And this is the real completion of my talk. I have no idea how much time I've taken. I'll give you the conclusions. I'll give you the conclusions, and then we'll discuss it, and then I hope we get some vigorous questions. Okay. First of all, I talked about this Rayleigh-Taylor. I didn't go into all the details of exactly how you do it. But the important point I want to leave with you, if you understand the mechanism, and you understand the fact that the Rayleigh-Taylor wants to twist the flames at the flamelet scale, that the twisting action or the injection of the twisting and the mixing process is maximum at the twisting scale. If you realize that at that scale, now all of this, all of the fact that the heats, the radiant fraction, the incompleteness of combustion, and the volumetric heat release, all of these being constant, all of these for pure buoyant flames becomes obvious. Okay, it just becomes obvious. So it is. That's the key. All right, and I haven't derived and shown you all that, but you have to enter into that and realize that. And when you get, and it leaves me very excited because when you actually can get something that is obvious, it really means it's very satisfying. My original creeping flame spread work. It wasn't obvious for years. Okay. This is the smoke point. That's an empirical relationship. I showed you that. I gave you some interpretation. We provided a diagrammatic relationships in terms of temperatures. We expressed this with a mathematical model with some equations, and we get chi-r and chi-I. We get an excellent comparison of experiments for burning in air. We get a correlation. We can generalize this because we have very good empirical measurements, and they correlate nicely in general atmospheres. And then we have predictions of the flame radiation absorption coefficient in terms of these simple, well-known, relatively well-known variables. And so now we really, that absorption coefficient, if you know the path length, often when you want to get the radiation in a particular situation, you've got to know the path length, and you've got to know the amount of stuff that's radiating, and if you have the overall radiant fraction of the flame, you from the type of fuel that it is, etc., and when you have that, and then you have the absorption coefficient, you can begin to calculate radiant fluxes. That concludes the thing, but now I want to talk about what we don't know. Okay, what do we don't know? We don't have a good theory for pool fire burning rates. No. We've got hundreds of empirical studies of measuring pool fire burning rates. Hundreds out there. Literature is massive. But we don't have a good theory. Okay. This existing thing will tell us, knowing the absorption coefficient, we can begin to turn into it's not totally simple, but we know things. We can begin to apply it. Then you need that absorption coefficient to know how much that radiation is absorbed before it gets to the fuel surface. We need an absorption coefficient if we are to get wall fire heat radiation with a simple formula on wall fires. We need that. Okay. All right. What is surprising, that caused me years of delay, is I didn't have measurements of the incompleteness of combustion in general atmosphere, in diluted and oxygen-enhanced atmospheres from the FPA. It's just, we haven't got them yet. Okay? And this is a nice, simple thing. They have an FPA here. They could be measuring this, okay? And it would make a very nice study, okay? The incompleteness of combustion, that's a routine type of measurement. And I know all measurements are difficult, but it's been done. Many people they can get agreement, and so I call it routine. Okay. Now, this is a fascinating question. Okay, and Lou was the one who put me. Lou Grizzo. He'll talk to you this afternoon. He was. We have very large pool fires. Okay, of LNG, but they have a smoke mantle on them sometimes. And when they have a smoke mantle, they don't radiate as much. And the question is, what is that effect? Well, we don't understand it yet. We don't have a real model for this. We have correlations, but we don't have a model. And to give a deeper understanding. And now this is the biggest one. To measure and model the effect of wind on pool fires, for pool fire burning rates. Everything I talked about was pure buoyant. Everything. Okay, but many fires are influenced by the wind or I would say the vorticity coming into the flames. That vorticity is not being looked at by researchers anywhere near as they should be looking at it. And it's that vorticity that then causes the burning rates to change. It's the vorticity that is the key to understanding this. And so I think in the future, as we learn more about these flames, the researchers will be looking at vorticity, because the vorticity is going to tell us many new things, and many of the interesting things with the flame wiggles, etc., are all coming in from the vorticity. So there's a big area of fascinating work, and I think we've all looked at a fire in a fireplace and said how fascinating, how these wiggles work. You can't understand that without understanding vorticity. So that's my final comments. I hope I've made you work.
Okay, you happy to take questions then, John?
Sure.
Okay, before we do our medal. So the interesting start to the proceedings this week. So has anyone got any questions? Everyone a bit too stunned.
Great.
The extinction at the Soot point, that point height.
Right.
Is that dilution, radiative extinction? What's going on locally there?
Okay. It's. Let's put the picture up. Okay. At this point, this temperature, I and George Markstein measured it, and we got 1600 degrees Kelvin. Other people have gotten 15. Okay, I'm not going to argue about that. Okay, but the important point is that this flame at this height would have the same temperature as this flame at the same height. Okay, if you measure the flame. The average effective soot radiation temperature, the average effective, we took a slice and measured the horizontal slice through there, the temperature. So we know that the oxygen can't react if it drops below the air. The oxygen in the air doesn't react if that temperature drops below 1500 degrees Kelvin, or 1600 degrees Kelvin. So the oxygen turns off there. Okay, and therefore anything beyond that, up to this point, diffusion is controlling. It's the diffusion of oxygen that's controlling. The oxygen gets there, but if it doesn't get tickled enough by the heat and the other things, it won't react. Okay? It doesn't decompose, and therefore it can't react with the soot.
So,
You have a strong enough voice.
most other extinction situations, the same 1600 degrees applies,
Right.
but the flames are typically blued out and, not copious amounts of flame. Yet we seem to have the same thing
Okay.
going on in different places.
Okay. If you have, if you take a fire, okay, all right, and let's say you have PMMA, and you burn it in an atmosphere that is vitiated with nitrogen. As you drop the temperature down to 1500 degrees Kelvin, everything turns blue. Okay? Maybe a little bit before that, but it all goes blue. Why? Because the soot doesn't form. The soot is a function of temperature. The soot formation rate is a function of temperature. So that is very clearly a temperature-dependent thing. You do not get no meaningful soot forms, okay? And so therefore the flames are no longer luminous, they're blue, right? And that's a very distinct thing. And this is with many fuels, okay? Now, so that's what's happening. Now, you've done some nice work where we have, 1713? If you have a stoichiometric temperature dropping beneath the 17, the flames tend not to burn. That's very nice work. And I don't think this is necessarily all that inconsistent, but that number is there for those. A premixed flame won't burn if it's adiabatic temperatures below 17 something. Okay. That's not really what we're dealing here. We're dealing with the oxidation of soot. We're dealing with the buoyant turbulent flame, or oxidation of soot in this case with these flames here. Okay? Got it. Hello.
If you look at the parameter mu, it sometimes becomes negative. I was wondering, what is the meaning of a negative mu?
The meaning of negative what?
Mu.
Oh.
Parameter mu.
All right. If mu is negative, it means that the psi chemistry, CH, is less than unity. Okay? That's what it means. Right? And it means that, I have to think, I'm sorry. It's a good question. I don't have an immediate answer. It's a good question. I don't have an immediate answer. Okay? I don't want to say something wrong.
Okay, thank you.
That sounds like one of the classic questions that needs to be discussed later during the coffee break.
I have to think about it. Okay. It's a very important question. I've asked myself that question, and it took me a long time to understand the meaning of mu. It came out of the experiments. It came right out of the experiments. I knew that mu was the key thing, because if chi r, if chi r is equal to mu, it means that you just is the borderline of not forming incompleteness of combustion. Okay? So I know when chi r equals mu what it means, but when mu actually equals 0, I don't have a simple interpretation.
Okay, I think we're going to go to a close. I think time's ticking on. So thank you very
Good.
much, John. Well, it is now my great honour to present John with the Rasbash Medal, which is, for those who've never seen one, is a picture of Rasbash. looking very typical. So
Like David.
That's right, exactly as you remember him, or those of us who remember him remember it. And it's, I think we're very pleased on behalf of the IFE to present this to you.
Thank you very much.